Hello, welcome to today's lecture on neural learning. We'll be covering these following topics where we'll start off with perceptron learning, then we'll proceed on to optimization, then I'll explain gradient descent, sigmoid unit, and then we'll cover the topic of backpropagation. So if we are talking about a single perceptron looks something like this, where x0 is a bias term, and while x1 to xn, these are features that represent x, right? All of these x1 to xn are associated with weights which are unique w0 to wn, right? So you have x like this, these are the features, and these features have weights associated with them. So these all of these weights and your features are then summed into a single entity using a summation function, which is sigma, right? So this is a summation function which groups all of these x0, w0 till xn, wn and adds them into a single quantity, right, where I goes from 0 to n. Now when we calculate this summation is then presented to a step function, right? The step function outputs O such that x1 to xn is equals to plus 1 if sigma of wi xi is greater than 0 and minus 1 otherwise, right? So this would be greater than equal to 0, right? Now if you want to write it in a vector notification where w and x can be represented as vectors, right, where w can be written as a vector of length n plus 1 which starts from w0, goes on to wn, so the size is n plus 1, right? Similarly, we have x, which is made up of features and this bias term, right? This can be written as x0 till xn, right? Therefore, this output that is given by our perceptron can then further be written as is equals to plus 1 if dot product of w and x is greater than 0 and minus 1 otherwise. So this consists of your simple perceptron, a single perceptron unit. Now the thing to notice is when we are considering this perceptron unit, this whole thing, the one marked in red, makes up our single node, right? Now when we talk about multi-layered perceptrons, those are basically made up of such single nodes all grouped together connected through weights. All right. So now the idea behind perceptron is simply that we have to learn a good set of weights, right? If we have a good set of weights, then we have our output as close to our target variable that we need to classify, or that we need to predict, right? So the learning is simply an iterative weight update scheme, right? We get our output, we present our features, we get our output, we compare our output to our target variable or our target function, we see that there is a difference. So what we do is we backtrack and we update our weights. So simply perceptual learning is updation of weights. It's iterative weight update. So what do I mean by iterative weight update? Iterative weight update would be for each wi, we update that wi with a certain delta wi, which is calculated using our features that are presented, that is a particular feature xi multiplied with a learning rate. So this neta is called learning rate, and this ranges between 0 and 1. So basically our delta wi depends on our misclassified examples, right? What do I mean by misclassified examples? Let's see, if our example is misclassified, only then we would need to update our weights, right? Otherwise, if our perceptron is able to classify a certain example correctly, that means we have a good set of weights, that means our algorithm has converged and we can stop our training there, right? So this delta wi depends on a learning parameter and the input feature that we have. This learning rate is basically a smoothing parameter which does not let your gradients to explode, right? So this is basically which modulates delta wi. So now let's take an example where I'll show you how we update the weights. All right, so let's take an example where let's say we have an xi which is misclassified as a positive sample, right? So that means the output of our algorithm is equals to +1, or the perceptron is +1. That it, our xi should have been negative, but it is misclassified as a positive sample. Therefore, the output that is given by our perceptron is equals to +1. And we see as we matched our output and our target value, we saw that there is a discrepancy. That means it is a misclassification, right? So now what we do is, if we have yi is equals to +1, that means wxi is less than equals to t, where t is some threshold which describes our decision boundary, right? Yeah, so basically till now, where we explained regression, classification, what we were doing, we were trying to build a decision boundary to separate two sets of examples, right? So in this also, using perceptrons and neural networks, if we're using for classification, what we're trying to do is we're trying to build a decision boundary that separates the two sets of examples into their respective classes. Right. So you might be confused, like, what is this? So this is nothing but, let's say, we have two sets of classes, positive and negatives. Right. Let's take one negative sample here. All right. So now our perceptron has built a decision boundary such that we have a misclassification. Right. This is xi. It should have been negative, but it is misclassified into positive class. So everything above is positive, everything below is negative class, right? So we see that as it has been classified as a positive example, we see that wxi obviously is less than t, right? So if we want to move this decision boundary above this so as to bring it someplace here, so that our classification of the two classes is perfect, what we need to do is we need to get a w dash such that w dash xi is greater than w into xi, right? Hence moving the decision boundary towards xi or possibly above it, right? So we need to calculate a new weight vector, right? So this is achieved by calculating a new weight vector such that w dash is equals to w plus eta xi, right? Where eta ranges between 0 and 1, right? So if we replace this value of w dash back here, we get w dash xi, it would be equal to wxi plus eta times xi into xi, right? Now as we know, this term would always be positive because this is a square and eta lies between 0 and 1, right? So as this is always positive and we are adding a positive term to wxi, that would mean w dash xi would be greater than wxi, right? As required. That means we have shifted a decision boundary above by eta xi, right? So okay, let's take another example. Okay, so let's take another example where let's say we have an example xj. All right, we have an example xj and it should have been classified as a negative sample, but it is misclassified as a, sorry, it should have been a positive sample, but it is misclassified as a negative sample, right? If it is misclassified as negative sample, that would mean our yi is equals to -1, right? Wxi would be greater than t. We would need a certain w dash such that w dash dot xi is less than wxi, right? Because we need to push our boundary down, right? This was the positive and this was the negative class, and our decision boundary right now is somewhat of this sort, right? And we need to push this boundary down so as to get a decision plane here, so that both of these classes are distributed properly, right? Now, in order to do that, what we need to do is, let's reduce eta xi from our w, right? So this would lead to, this is all xj, we are taking a different sample, so these are all xj's. Okay, so w dash dot xj would be equal to wxj minus neta xj dot xj. As you know, this is always positive, and we are subtracting a positive value from a whole value. That would mean w dash dot xj is less than wxj. That is what was required. That means we were able to push our decision boundary downwards in direction of that positive sample or below it in order to get the correct classification. Now, to simplify it further, every time we have a misclassification, we don't need to calculate our w dash. We can shorten it down, these two rules, and we can combine them into one single rule where w dash is equals to w plus eta yi xi. Right, I'll explain why we have shortened it down to this. Okay, so this basically makes up your basis of Perceptron learning algorithm. Right, now how did I combine both of those rules into this one single rule? That is simple, right? When we had a positive sample misclassified into a negative sample, right, positive xj was misclassified as negative sample, that means we had yi as equals to -1, right? If you place the value of yi back here, what would we get for this particular sample? We would get w dash is equals to w minus eta xi, right? Similarly, if we have a negative sample xj misclassified as positive sample, right, therefore that would mean our yj is equals to +1. Replacing this value of yj back here, we would get w dash as w plus eta xj. Hence, it does the work of both the equations. So this gives us the basis of our perceptron learning algorithm, which simply, if I want to write an algorithm, it would be, okay, till algo converges, right? Till it has not converged, we'll continue our loop. That is for I, for each sample in our data set, right? Okay, if, now look carefully, yi w xi is less than 0, then w gets updated with w plus eta yi xi. This is because this will only occur when there is a difference between xi and yi. That is, xi is positive, whereas classified as negative, that means there is a difference here, right? Similarly, if we have xi as negative and yi as positive, we have a difference here, right? These are the only two cases where we'll get yi w xi less than or equal to 0. If we have that, we update our weight, right? We put converged as false because our algorithm has not converged and we are still getting our misclassified examples, and we keep on doing that. So we end this algorithm like this. So this ends when there is no more misclassified examples in our data set. Okay, so let's talk about optimization of our perceptron algorithm, because this can go on, and what we need to do is we need to quickly reach to an answer that is as close as to the correct answer, right? Because this convergence, like sometimes algorithms do not converge and they keep on going. So but we need a definite answer at the end, right? So for that we use a few optimization techniques, right? For optimization, because sometimes in our algorithm we need to reduce or minimize our loss function or our error function, right? For that we can use gradient descent. That is a very good example. I'll explain it in more detail. Sometimes we would need to maximize a function, right? That could be probability or likelihood. So these are the few like kind of optimization techniques that you can use on your algorithms to get a better result. Okay, so that brings us to our next topic of gradient descent. Right. In order to understand gradient descent better, what we need to do is we need to consider a simple linear unit, right? Where the output of the linear unit is defined by W naught, or like I'm taking X naught as one or the bias term as one, right? So we have n features and n weights associated with these features. Okay. So if we want to learn our WIs or we want to modify the values of WI, we need to reduce our error, right? And in order to reduce the error, we need to update our Ws. So let's learn WI that minimizes squared error, right? So if you're considering squared error, and O of D stands for output for a particular sample, and TD stands for the target value for that particular sample, right? So if you're considering squared error, we get error on W as half of, what would it be? It would be simply the difference between the target value and the output value squared divided by 2, right? Where D is the set of training examples, right? So in order to optimize this, we need to differentiate our error term with each of the W's, right? And depending on these values, we need to update our weights, right? So in order to do that, let me draw a graph so that you can easily understand it. So we'll be proceeding with this only. We need to find dE by dWi, right? And use this, minimize this, because this would reduce the error and we'll get a new value of W, and that value of W would be used to update our weights, right? Right. So if I'm talking about gradient descent, and let's take if our error depends on two terms, W0 and W1, right, we would get the error function, something of this sort. This is like basically a bowl, right, a huge bowl, and it has a global minimum that is down at the center, right? So what happens if you roll a ball from here? If you roll a ball, it will eventually find, it will go down till the lowest point, it will oscillate up and down, and finally it will settle down at the minimal position or the global minimum that we have, right? So in order to get our point to the global minimum, or to reduce the error to the minimum point that it could go to, what we do is we take the partial derivation of our error with respect to W0 and W1, that is the gradient, and delta E that we calculated, that stands for gradient vector, right? So this gradient vector basically tells you the direction of steepest increase of E, right? So if we want to get the steepest decrease, what we need to do is we need to take the negative of this gradient vector, right? So this gradient vector gives the steepest increase, right? So in order to find the steepest decrease, because we need to decrease it down to global minima, right? In order to do that, we need to take the negative of our gradient vector, right? So this gives us, if you want to calculate a delta W, delta W would be given as minus eta delta E of W, right? So that brings us to delta Wi is equals to minus eta dE by dWi, right? Where E was half of TD minus OD squared sigma. So delta Wi is given as minus eta d by dWi half of sigma TD minus OD squared, right? So this gives us delta Wi is equals to minus eta half dWi TD minus OD squared, right? So let me just remove this part. It's all clear till this step, right? It's all clear till this step, so I'll just remove it off and continue. Now differentiating TD minus OD squared, we get half, okay, so we have eta as well, half eta sigma twice of TD minus OD, right? Applying the chain rule, simple chain rule, dWi TD minus OD, right? So now as we know, TD is our target value and it is constant. So differentiating it with respect to Wi would give us 0. So this brings us to, we have a negative sign as well, eta. So this 2 gets cancelled. We get left with sigma of TD minus OD, right? D of dWi, TD is 0 and our OD can be written as WXD, right? So after this step, differentiating both of these terms, we would end up with sigma TD minus OD, d by dWi of TD is 0 and d of dWi of minus WXD would be equals to minus XD, right? So this gives us minus XD. Therefore, dE by dWi is equals to eta sigma TD minus OD minus XD. So how does this calculating of DE by dWi helps us in getting the steepest decrease, and how do we get our error to reduce to the global minimum, right? So in order to do that, what we do is we initialize each Wi to some random variable, right? So we initialize it to some random values, initialize randomly, right? After we do that, we put delta Wi as 0, right? For each training set, training sample, and for each linear unit weight, right? So for each linear unit weight, that is basically from W0 till Wn, for each weight, we need to update, or we need to calculate our delta Wi as delta Wi plus eta, where this is the target value and this is the output value for that particular data sample. And for each, then after calculating this delta Wi, for each linear unit weight again, we update Wi as Wi plus delta of Wi. So this gives us our gradient descent, right? So now there are two types of gradient descents, or like there are like actually multiple types of gradient descents. In this we discuss about two. That is number one is batch gradient descent, right? So in batch gradient descent, what happens is we run our training algorithm or the perceptron algorithm over the whole data set. We calculate the error at the end, and then we proceed to update our weights, right? So in this, we take the whole set, we run the training algorithm on the whole set. When the error is calculated, this error depends on all of the values in the data set, right? And using this, applying the gradient descent, we update W's after we have run through the whole set. And the second type is incremental SGD, or incremental gradient descent, right? In this, for we proceed to update our weights for each training example, for each misclassified training example, right? So we start off with the first sample, we try and classify it, we compare T and O, that is our target and the output. If it is misclassified, we update the weight, and then we proceed on to the next sample instead of taking the whole sample at once, right? So in incremental gradient descent, we take each sample, for each sample we update the weight if required, and the error now just depends on the target value and the output value of that particular sample, right? For that particular data sample D, right? It is also called stochastic gradient descent, SGD, where S is stochastic, right? Which means the samples are selected at random, right? So this is basically random selection, but it runs over the whole data set. Well, this SGD, because if you take the batch gradient descent, and if you have a very large data set, you'd have to wait for the algorithm to run on the whole data set, and then you'd need to update your weights. So this incremental gradient descent is really helpful when we have a large data set, because we can keep on incrementing or decrementing our weights accordingly and according to each data sample. So this brings us, we have discussed perceptron learning, we have discussed gradient descent. Now comes sigmoid unit. Now what is sigmoid unit? Right, as we saw in the perceptron, after summation of w naught x naught plus w1 x1 till wn xn, it was then presented to a step function which was classifying into +1 or -1. Right. Instead of just classifying that sample into two particular data classes, what we do is we introduce a sigmoid unit instead of a step function. Right. So we have the same setup as before, right? We have a set of features till xn. We have all of these features associated with particular weights, right? All of these values are then presented to a summation function, where let's call it net. It calculates sigma of wi xi, where I goes on from 0 to n, right? Now after this net is calculated, instead of presenting it to a step function, we present it to a sigmoid function. Okay, so now what is sigmoid function? Sigmoid function, let's describe it by using sigma, the basic symbol for it. Sigma of x is 1 upon 1 plus e to the power minus x, right? Therefore, using a sigmoid function in this case, what we would get is sigma of net is equals to 1 upon 1 plus e to the power minus net, right? The value of sigma, as you can notice from the graph, it ranges between 0 and 1, right? Now, why do we use a sigmoid unit or a sigmoid function in our perceptron? Because of its mathematical brilliance. Let me show you. So the logic behind using sigmoid function is because of its nice property that when you differentiate sigma with respect to x, what you get is sigma of x into 1 minus sigma of x. You can do it mathematically. You'll find out that the result that you get is finally this. Okay, so now if you're considering multi-layered networks or multi-layered perceptron units, we would need to introduce the concept of backpropagation in it, because there are many hidden layers, and the difference between the input layer and output layer, there are many different weights and many different units that are associated. So we would need to update all of those weights depending on the output that a multi-layer perceptron would give out. So again, in this sample, we would start by assuming that we want to minimize our squared error, right? So our error is defined as 1 by 2 sigma td minus od squared, right? We want to reduce this error, right? So we need to differentiate this error with respect to wi's that are present uh, in order to update our weights. What do we get is d by dwi uh, half sigma td minus od squared, right? So you get half sigma td minus od squared, right? So we are just following the same steps that we did earlier, right? We get twice of td minus od d by dwi, let's take it in the bracket, td minus d of od upon d of wi, right? Where this is equals to 0, right? So in the end, we get left with, let's cancel out 2, we get left with sigma of d td minus od negative of d of od by wi, right? It's clear till here. Let me just remove this part. So we have reached this point. Now d of od by dwi can then further be written as, this is td, this remains the same, this can be written as od upon d of net by dwi, right? And where our net was basically sigma of wixi, right? The summation. So now look closely. If we are to consider d of od by d of net, right? What was our o of d? What was the output of a perceptron? Our output of the perceptron was sigma of net. That was equals to 1 upon 1 plus e to the power minus net, right? And if we differentiate O of d with respect to d of net, so we would get, right, which is similar to, right? And what was the result? We got the result as this. So now if you're considering d of net, sigma of net, right, and we're differentiating it with respect to net only, we would get as a result 1 minus O of d, right? Pretty straightforward, pretty simple. We're just differentiating it with respect to net, and if we do that using the property of our sigmoid functions, we get sigma of x 1 minus sigma of x. That would be equals to sigma of net into 1 minus sigma of net. And what is our sigma net? Sigma net is O of d. So this can further be written as O of d 1 minus O of d, right? Now, so as we have calculated the first part that we needed as, okay, let's remove this part, and we get left with this is equals to O of d 1 minus O of d, right? And our net was sigma of wixi. Now differentiating net with respect to wi, and let's write this in terms of vector. This can be written as wx for that particular data set d, right? Now differentiating net with respect to wi, we would get d by d of w, now which is equals to x of d, I comma d. Let's write it as I comma d because we are talking about a particular wi. So that means our second term is equals to I comma d. This brings us to differentiation of e, partial differentiation of e with respect to wi would result in, oh, we forgot the negative sign here because it was minus dod by dwi. We get td minus od into od into 1 minus od x I comma d. Right, this is the result when we're using a multi-layer perceptron. Now let's explain how do we use backpropagation. So as we have calculated our delta E by delta Wi, now comes to the topic like how do we use that in our backpropagation. So let's say we have a net, something of this sort, right, where each of these units are interconnected, right? So each of these units are interconnected, and this is our output layer K, and this is our hidden layer H, and this is our input layer, right? So let's just consider a 3-layer perceptron. So if you want to understand backpropagation or apply backpropagation, the number one step would be to calculate the output of our network. First, we need our OD so that we can compare it to our target value, right? So number one step would be calculate output of network. Now, once we have calculated the output of the network and we see that there is a discrepancy between TD and our OD, so in order to reduce the difference between them or reduce the error, what we need to do is we need to update our weights by going time but backwards, right? So once you've calculated our OD, we need to find for each hidden unit, or sorry, each output unit, unit K, right? So these are our output units. We have 2 output units in our hidden layer. We need to find or calculate delta K, which is defined as O of K minus O of 1 minus O of K, Tk minus O of K, where O of K is the output of our network. Once we have done this, we need to proceed to our hidden layer, right? So for each unit H in hidden layer, we need to calculate delta H, which basically depends on the value of our delta K, right? For each KH, it gets multiplied to delta K. So if this is K, this is H, this is basically KH, because we are talking about going back, right? So once we have calculated for each hidden unit H, and we have calculated for the each hidden output unit K, what we need to do is we need to update our weights now. So number 4th step would be to calculate delta Wji, which is given as eta delta J x Ji, right? Where J would be equals to K if we are talking about the output layer, and it would be equals to H if we are talking about the hidden layer. Now once we have calculated our delta Ji, we need to update our weight. That is equals to Wji is equals to Wji plus delta Wji, right? So for each misclassification, we need to follow these steps in order to update the weights in each of the, between each of the units, right? So now once we are done with backpropagation, we might see that, okay, our error function could be described in a way that, let's take our error function like this, or let's start with this. All right. So let's say if we want to calculate our global minimum, this is a global minima, and these 2 points are our local minima in the graph, because these are the lowest possible values in the locality, right? So let's imagine we start rolling down a ball from here, right? So if we roll down the ball from here, it will get to this point, it will come down, and it will get to the local minima point right here. After this, it sees that on both the sides, its steepest increase in slope. So it would think that it has, the algorithm has found the global minima, whereas it has just found the local minima, right? So in order to stop our algorithm from doing this type of error where it finds the local minima instead of global minima, we introduce the concept of momentum. So momentum is defined as alpha, which basically gives this ball the little push that it needs to get over the slope. Right? If it gets over the slope, let's say it comes here, it again sees that, okay, all right, I find a minima, but it's not sure that it's local or global, right? So again, the momentum gives it the necessary shift or the push that it needs to get over this particular slope, so as it reaches our global minima and converges to the correct point, right? Now, how do we incorporate this alpha? This alpha is incorporated when we calculate delta wji. Let's say we are in nth time step, or we're talking about the nth example, or we're going into the nth iteration for our training, right? So if you're going in the nth iteration, this is iteration number, we calculate delta wji as eta delta j xji. Now in this, what we do is we introduce momentum such that we introduce a new term delta wji of iteration previous, multiplied with alpha, added to the original delta wji that we had to calculate the new delta ji, right? This particular term will give enough momentum to the ball to get it over the local minima, right? So this is basically previous iteration. So using the value of the delta w from the previous iteration, we multiplied with alpha to find the global. Right. So there are many forms of smoothing or corrections that are needed, or hyperparameter tuning that are needed for a neural nets. So one such thing is regularization. Right. So regularization helps when our network is underfitting, so or overfitting. So regularization makes our model less likely to overfit, but this could lead to underfitting as well. So what regularization does is it increases the magnitude of our weight vector. Increases magnitude of our weight vector. How does it do it? It does so by introducing a term gamma sigma w square. Right. So I think we have seen it before. It is given as half. Don't get confused by double sigmas. This is just between, because it's between two layers. Kd gamma. Right. So this additional term increases the magnitude of our weight vector so as our model does not overfit. Right. So there are other ways that can be used, such as weight decay and shared weights, etc. So all of these techniques can be used in order to stop our models from underfitting or overfitting. So next we face the problem of underfitting or overfitting, right? So overfitting is basically a modeling error that occurs when the function is too closely fit to a limited set of data points, right? So as you can see, the error, this is error, and this is, I think, our iteration, right? So you see, for normal training set, the error gets continuously reduced, right? While as for validation set, it initially reduces, but then it plateaus and then it increases, right? So this means that our function is very closely fit and it is overfitting the data, right? Similarly, in underfitting, right? In underfitting, you can see the error going down on training examples, the training data set, while it initially decreases for validation set, but then increases and it fluctuates basically, right? So if you want to understand this, let's say with on the basis of an example, Okay, so let's try and build our example. Let's say we have this two axes, right, where we have some crosses, right, and some zeros, right. So let's say we have something of this sort. All right. So let's talk about underfitting first. Underfitting would be like we are taking it too general. So taking it too general is let's say we just build a straight line through it, right? So this would be considered as an example of underfitting because our final formula or the algorithm is not closely related to the data points. It's very general, right? So if we want to talk about, let's say, overfitting, overfitting would be our function that we made through perceptrons is very closely related to the data. All right, and if it sees a new data set, it is not able to properly classify it or percept it. So if I take the example of overfitting, overfitting would be something of this sort, that it is very closely related to all the data points, right? This is the example of overfitting, and we want to avoid both of these things, right? We don't want to either overfit our model or underfit our model. So I would say like the right amount of appropriate fitting would be of something of this sort. I haven't drawn this to scale, so let's say something of this sort, right? Obviously it misclassifies one or two examples, but that is acceptable, right? Otherwise it will overfit or underfit. So this is the appropriate fitting. This is the kind of fitting we want. Like I know there are like couple of examples that are getting misclassified, but it's okay. It's better than underfitting or overfitting, right? So this covers our neural networks lecture. So if you have any doubts, let me know. I'll see you in next class.